Section 10.1 The basic ingredients for testing with categorical variables. For these sessions, we'll be introduced some basic ingredients for testing with categorical variables. And then section 10.2, we're going to combine everything together to do the hypothesis testing. Let's look at this example. Suppose we want to determine if a standard 6-side die was fair. In a perfect world, if the die was fair, the distribution of outcomes would look like this. So this is the probability distribution of the outcomes. We have the fair 6-side die here. So they do have the same probability to land on each numbers, right? That would be 1/6. Now, we're going to perform an experiment. We're going to roll this die 60 times and record the number of the spots. The outcomes are shown in the table and the graph below. So you can see this is the outcome. I can have number 1, 2, 3, 4, 5, 6. And then the frequency. This means when I roll the die 60 times, I do have the 12 times to get on 1, 8 times to get on 2, 10 times to get on 3. Okay, when you add it up, these numbers, it should be equal to 60 times. And also, I will use the probability distribution to represent this outcome. So when you guys compare these two outcomes, we can see that the outcomes were not exactly what we could expect in a perfect world. We will use a statistic called the chi-square statistic. Please highlight this one, the chi-square distribution. Okay, from the chapter 7, chapter 8, chapter 9, we introduced the Z distribution. We have the student T distribution. Now, this is the new distribution called chi-square distribution. And we're going to use the chi-square distribution to compare the real outcomes with the expected outcomes. And we use the chi-square distribution to find the p-values. That tells us whether we should be suspicious that our outcomes are not matching our expectation. First, expected counts. The expected counts are the numbers of observations we could see in each cell of the contingency table if the null hypothesis were true. We do have two types of expected count. First one, all expected frequency are equal. That will be this one. All expected frequency are equal means they do have the same probability to land on the outcome here. Okay, so this is the first type of expected count. All expected frequency are equal. Second one, all expected frequency are unequal. Okay, I'm gonna talk about this one for the next slide. E will be the notation of the expected frequency. When all the expected frequency are equal, we'll be using this formula. E equal to n divided by k. What is the n? N is talking about when we roll the die 60 times, n equal to 60. And then the k, talking about how many characters do you have. In my experiment, I do have 1, 2, 3, 4, 5, 6. I do have 6 characters. So that will be 60 divided by 6. So it's going to be E will be equal to 10. This is called expected frequency. For all expected frequency are unequal, we'll be using this formula. Okay, E1 will be equal to n times the P1, E2 equal to n times the P2, and so on. Okay, now let's look at the example. In our previous example of the fair die, if the die is rolled 60 times, we could expect 10 of each outcome. The table below shows the expected count and the observed count from the experiment. Okay, expected frequency. So this is talking about in the real world, we should have a 10 times of 1, 10 times of 2, 10 times of 3. All right. Observed count, this is talking about from our experiment. When we roll the die like 60 times, I'm gonna record the number that I get for each of them. Okay, so you're gonna see we do have all expected frequency are equal. We're gonna use this formula. Okay, expected frequency will be equal to n equal to 60 divided by 6 because we do have a 6 categories. And that's why my expected count will be equal to 10. Okay, right? Now, when we have all expected frequency are unequal, okay, this is a biased 6-sided die. It means some numbers are more likely to be rolled than others. So they don't have the equal probabilities on each number. And we call this as expected frequency are unequal. Okay, so again, observed frequency. This is talking about when you perform the experiment. And then we're going to record the result here. And then probability. This is talking about for your biased 6-sided die, you do have a 25% chance to land on 1. You have a 10% to land on 2, 12% to land on 3. So from here, we're going to know this expected frequency are unequal. So we're going to apply this formula. E1 will be equal to n times P1. The n talking about observed frequency for 100 volts of a die. So means we're going to roll the die like 100 times. So n equal to 100 and then P1 talking about the probability in here. Okay, so we have a 100 times 0.25, which is going to be 25. So this is going to be my expected frequency here. Okay, we're going to do the second one. Okay, right, 100 times 0.10, that will be equal to 10. I'll let you guys finish the rest of them. Okay, check on your work. You should have this one. Okay, A, no matter you have expected frequency are equal or expected frequency are unequal, when you add it up here, add up this number, it should be equal to your n here. Okay, so double check your work. Second, let's talk about the contingency table. Summary table that displays frequency for outcomes when two categorical variables are analyzed. Even though there are numbers in the table, these numbers are summarized of variables whose values are characteristics. So contingency table, this is when you have two categorical variables, okay, and then they may have the relationship on each other. Okay, and this table, even though we use the number, this is not the numerical variables. Okay, look at this example. This is a contingency table, or you can call this as a two-way frequency table. And this table consists of frequency counts or categorical data corresponding to two different variables. So one variable is talking about like gender. We have a male or female. And one variable that is talking about smoker. Okay, you are a smoker or non-smoker. Okay, so from this table, you can see we do have a 14 males as smoker. We have a 11 female as a smoker. And we have a 17 male as non-smoker. Okay, right? So first, I want you guys try to find out the total here. How many males are here? How many female are here? And then how many smoker? How many non-smoker? Okay, check your work. Add it up. We do have a 31 male here. And we have 30 female. We have a 25 smoker and 36 non-smoker. Okay, when you add it up from the row or also the column here, you could see the total, we do have a 61 here. Okay, 61, that will be our sample size. And we call that's the grand total. Okay, grand total. So double check your work when you add up the last row here or add up the last column here. This is called the grand total. Okay, when we have a contingency table, how can we find the expected frequency? The formula for the expected frequency will be the row total times the column total and divided by the grand total. And this is going to be your grand total. For example, I want to find the expected frequency for male smoker. Okay, smoker and the male. So I'm going to draw two lines here, male smoker. So I use the row total times the column total. So 25 times 31 divided by grand total, which is going to be 61. Use your calculator, that will be 12.7. Okay? Now, second one. I want to find the male non-smoker. Okay, male non-smoker. So it's talking about this part. So that will be 31 times 36 divided by 61. So you're going to get 18.3. Okay, I want you guys finish these two also. Find out the expected frequency. Okay, you're gonna get these two. So this is the expected frequency. You're gonna see I put E11. E11 talking about here, first row, first column. E21 talking about second row, first column. And then I try to rewrite it. Okay, I'm gonna put the parenthesis here. This is represent the expected frequency. Okay, right? You guys need to know how to find the expected frequency in the contingency table. Okay, in the chapter 7, chapter 8, chapter 9, we introduce the standard normal distribution, the Z distribution, and the student T distribution. Alright? Let's review a little bit. Okay, both distributions are symmetric. Okay, symmetric. When you draw the line in the middle, the left-hand side is roughly equal to the right-hand side. So this is symmetric, and it is more spread out than the standard normal distribution. This is talking about the T distribution, okay? And if we increase the number of the degree of freedoms is only for the student T distribution, okay? If we increase the number of degree of freedom, the student T curve become closer. So when you're working on the T distribution, you need to find the degree of freedom, which is gonna be n-1. When you increase the sample size, you will be increase the degree of freedom, and the T distribution will be really, really close to the standard normal. Okay, right? So this is standard normal distribution and the student T distribution. And for these sessions, we'll be introduced the new distribution. This is called chi-square distribution. Okay, chi-square. It doesn't mean you're gonna take square for this number. Okay, this is just the name, chi-square distribution. Chi-square distribution denote chi-square, pronounced chi. Values of the chi-square statistic are always greater than or equal to 0. So you could see we don't have the negative numbers. Okay, chi-square is always positive. Unlike the Z distribution and T distribution, we do have a positive values, and this is going to be the negative values. Chi-square distribution are not symmetric. They are skewed to the right, unlike the normal and the student T distribution. You can see they will be skewed to the right usually. Has the number of the degree of freedoms increased? That's the same idea with the student T distribution. Chi-square distribution, they do have the degree of freedom n minus 1. When you increase the sample size, you will increase the degree of freedom. Then the chi-square distribution approach a normal distribution. You're going to see this one. Okay, it looks like the normal distribution when you increase the sample size. Okay, chi-square statistic. The chi-square statistic measures the amounts that our expected counts differ from our observed count. Formula for the chi-square statistic is, this is how you guys finding the statistic. We'll be using the chi-square distribution. The O represent the observed value. E represent the expected value. Okay, and this is gonna be the summation notation. You're gonna add it all up. Okay, right? Let's try an example to find the chi-square statistic. Okay, we're gonna use the previous example here. We have the gender and the smoker here. And we already found out the expected frequency. So now let's try to plug into this formula. Okay, like the first one here. The O will be 14. This is the observed frequency. Minus expected frequency, take square, divided by this guy. Plus the second one. Observed frequency 11 minus 12.3, whole thing square, divided by 12.3. Okay, so we have 1, 2, 3, 4. You should have this guy. You can plug in into your calculator to find it out. You're gonna see 0.458 here. This is gonna be the chi-square statistic. Okay, right? Okay, I want you guys try to do this example by yourself. First, find out the total and then find out the grand total. And then find out the expected frequency and then find the test statistic. Okay, let's try to work together. In the research poll, there are two categorical variables. Background, the US adult or scientist, and belief in safety of GMO. Find the expected frequency and chi-square statistic. So first, find out the total. Try your work. Okay, you do have a grand total for 200. Now, let's find the expected frequency. First one, we're gonna find the E11. So we're gonna use the row total times the column total divided by grand total. Okay, E21, so that will be this guy. 75 times 100 divided by 200. Okay, E12 and E22. So find out the expected frequency. And then I'm gonna write it here with the frequency. Okay, right? Total, grand total, and expected frequency. Now, I'm gonna use the formula to find the chi-square statistic. Plug into the formula. You should get 55.488. So this is the basic ingredient for the categorical variables. And in session 10.2, we're gonna combine everything together to construct the hypothesis testing. That's it.